Alright, so this is on section 6.12, which is on fixed level testing. So a lot of these are going to be recalls. So let's first recall alpha is the value between 0 and 1, which is called a significance level. If it's not specified, the default value is alpha equal to 0.05. And so we conduct a hypothesis testing and we compute what's called a p-value. And there are two cases. If p is less than or equal to alpha, then we can reject the null hypothesis at 100 times alpha percent level. And because we reject h0, so we can accept h1. And case 2 is if p is greater than alpha, then we cannot reject h0 at this level. And because we don't reject h0, so we cannot make a conclusion. Okay, so let's quickly do an example here. So let's consider a sample with sample size 100, sample mean is 53, and sample standard deviation is 20. And we want to do the hypothesis test with mu less than or equal to 50 versus mu greater than 50. So the null distribution has mean 50 and variance being the original variance divided by the sample size. So the variance is 4, which tells us standard deviation is 2. So mean is 50. Our x bar is 53. To calculate the p-value, first we calculate the z-score. So z is 53 minus 50 over 2, which is 1.5. And you look at the z-table, you can calculate the p-value. So the p-value is 0.0668. So depending on the value of alpha, we can make different conclusions. So we can reject h0 at 10% level because 0.0668 is less than 10%. But we cannot reject h0 at 5% level because 0.0668 is greater than 5%. Okay, so let's say I introduce a couple new terms. Okay, so two new terms, a critical point, not to be confused with the one in calculus, they're completely different. A critical point is the values of x bar yielding the p-value equal to exactly alpha. And the rejection region is the values of x bar yielding to rejection, which means the p-value is less than or equal to alpha. Okay, so let's use the example from the previous slide. So let's consider the null distribution being the same. The null distribution has mean 50 and standard deviation 2. And the hypothesis test is h0 is mu is less than or equal to 50 and h1 is mu greater than 50. Okay. Notice that critical point and rejection regions depend on value of alpha. So let's first fix value of alpha to be 0.05, the default value. So let's draw the normal distribution. Okay. So we want to calculate the value of x bar giving you p-value exactly alpha, which is 0.05. So basically we want to find a value here on the right that gives you area 0.05. But we have seen this before with one-sided confidence interval. If we want the area of the tail to be equal to 0.05, then this value here has to have z-score equals to 1.645. That's one of the two magic numbers that we need to remember. So if z is equal to 1.645, then x bar is equal to 50 plus 1.645 times 2, which is 52.29. So this is our critical point. Critical point. Critical point. And the rejection region, you don't have to do any new calculation. The green region, including the boundary, is the rejection region. So the rejection region is x bar greater than or equal to 52.29. So this is our rejection region. Okay, so let's do a slightly different example. So let's move on. So let's still keep alpha as 0.05, and no distribution is the same. It's still mean 50, and standard deviation is 2. But this time consider the hypothesis test being two-sided. So the null distribution is mu equal to 50, and the alternate distribution is mu is not equal to 50. So this time it's two-sided. Okay, so let's first draw our null distribution. Mean is 50. So we want first find the critical points, which yields p-value equal to 0.05. If we want a p-value to be equal to 0.05 for two-sided tests, then each side has to have an area 0.025. Okay, and we also should know this number because this is the number that gives you two-sided confidence intervals. So if area of the tail is 0.025, then the z score is going to be 1.96 and negative 1.96. So the critical points are 50 plus 1.96 times 2, which is 53.92. And the other one is 50 minus 1.96 times 2, which is 46.08. So these two numbers are our critical point. And the rejection region is x bar greater than or equal to 53.92 or x bar less than or equal to 46.08. So in general, the rejection region is the region outside the critical points. Outside and including the critical points. So if it's one-sided test, then the rejection region is one tail. If it's two-sided test, the rejection region is two tails. All right, so let's end the section with a couple more definitions. So in hypothesis, there are 4 possible scenarios. There's the possibility that we reject H0 and H0 turned out to be false. There's the possibility that we reject H0, but H0 turned out to be true. And 2 more possibilities. There's a third possibility we do not reject H0, and H0 turned out to be false. And we do not reject H0, and H0 turned out to be true. Okay, so there are 4 scenarios, and in 2 of them we made a right decision. So in the top left, if we reject H0 and H0 turned out to be false, then we make the right decision. And if we don't reject H0 and H0 turned out to be true, then we also make the right decision. But the other two, we make some sort of errors. So they have different names. So if H0 is true, but we rejected it, this is called a type 1 error. And if H0 is false and we do not reject it, this is called a type 2 error. Okay. So if we fix a significance level alpha, then there's a theorem says that, we're not going to prove it here, the theorem says that the probability of type 1 error happening is always less than or equal to alpha. So alpha is an upper bound for type 1 error. And regarding type 2 error, how about type 2 error? This will be talked about in the next section.